Taking a look at the second unit of, or not unit, sorry, lesson of organic when you're dealing with alkenes, so double bonds, and alkynes, so triple bonds. And when we have a double or a triple bond, the rules change a little bit, but not too much. So starting with the first one, you're still looking to identify your longest chain. So I would take a look at my longest chain here, and it wouldn't matter if I'm going this way or this way or this way, it will all be the same. But I do want to start my numbering over here for carbons to carbon 1, carbon 2, carbon 3, carbon 4, and I'll just make this one carbon 5. So I'm numbering based on containing that double bond in my longest chain. And I also want to start by numbering, giving the smallest number possible for that double bond. Then everything else will follow. So my longest chain is 5 carbons. So my root is pent. My double bond is between carbon 2 and 3. So you just say the first number. So carbon 2, there's a double bond, so it has to end in ENE. Now on carbon 4, I have 2 methyl groups. So I have to place that. So I'd write 4,4-dimethyl. And then it would be pent-2-ene. So this is number 2. So going through 4, you have to have both of those numbers to say that you're placing 2 methyl groups. You use the prefix di because there's 2 of them. So, and then methyl because this is just CH3. And then pent being the 5 carbons, 2 showing where the double bond is, ENE meaning there is a double bond. So that's 4,4-dimethyl pent-2-ene is the full name. Looking at example B, we still want to number our carbons, giving the smallest number the double bond. So it's either going to be 1, 2, 3, 4, or 1, 2, 3, 4. In this case, I'm going to number from left to right. The reason being is either way I went, my double bond was on carbon 2. So then I have to look at my side group. And I have this methyl group on carbon 2. So because I have a side group and a double bond on carbon 2, I'm going to go left to right. My longest chain is 4. So that tells me I'm at bute. I put 2 again because it's between 2 and 3, my double bond, and then ENE. Right, so this root 4 tells me 4 carbons in my longest chain, 2 between 2 and 3 is my double bond, and ENE just means there's a double bond present. Now I still have to name my side group, which is methyl, and just because there's 1 there, and it's on carbon 2. So this would be 2-methyl bute-2-ene. Now, looking at drawing is very similar in terms of what you want to start with. So when we are naming, you want to identify your longest chain. When it's drawing, I start by drawing out my longest chain. So here, pent-1-ene. Pent means I have 5 carbons. So 1, 2, 3, 4, 5. And on carbon 1, I have my double bond. So between carbon 1 and 2, I'll just add another bond. And then on carbon 4, so 1, 2, 3, 4, I have 2 methyl groups. So CH3, CH3. So once I've placed those, then my next part is to fill in my hydrogens if I'm doing the structural diagram. So on carbon 1, it already has 2 lines and carbon can bond to 4 atoms. So it still has 2 other atoms it can bond to, which will be hydrogens. Sorry, this is looking kind of funny. Carbon 2 can only bond to 1 other hydrogen, and it doesn't matter where you put it. It just has to be on carbon 2, so you can go above or below. On carbon 3, you have room for 2 hydrogens. On carbon 4, you have no room for anything else. And on carbon 5, you have room for 3 hydrogens. And now that one is done. Looking at example B, and this time I'm just do a line diagram to go a little bit faster. I again want the root first, which is oct, and then oct means 8. And on carbon 3, I'll have the double bond shown by ENE. So when I'm doing this in a line diagram, just remember every point is a carbon. So I'm starting at a point, so that's a carbon. So carbon 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Yes. And now on carbon 3, and in between 3 and 4, I need my double bond. On carbon 2, I need a methyl group. On carbon 5, I need a methyl group. 3, 4, 5. And on carbon 7, I need a methyl group. So line diagrams are a lot quicker if you understand them, but if you're still finding them tricky, just stick with the structural diagram and always try and practice the line just to get that understanding, because as you get better at it, line diagrams are just so much faster. Here's an old diploma question. Again, just showing we have that understanding about some terms and knowing the difference between single bonds and double bonds. So in this case, it does bring in something that looks like it's going to talk about the bromine test, but it actually isn't. Just knowing that hexane ending in ANE is going to be saturated, and then hexene ending in ENE is going to be unsaturated because you have a double bond. So here your answer would be B. Moving on to alkynes, if it's an alkyne, you have a triple bond. So for this first one, you have just 2 carbons, and you don't need to say where it is because you could approach from either direction. You'd have the same shape. It's the exact same compound. So this would just be Eth, meaning 2, and then end in YNE. Again, we don't need to say where that bond is because it's only one place to put it. If I look at B, you want to, again, identify your longest chain. So you have, I'm going to start on this side here, carbon 1, 2, 3, 4, 5, 6, 7, 8, 9. So your longest chain is 9. And just I want to remind you that your longest chain does not have to be a straight line. It's just how many carbons can you get without like lifting your pen. So, and you want the longest. So this was 9, and 9 is non. And you want to end in Y. Oopsie, I need to say where it is first. So your carbon 1, 2, 3, 4. So we still know it's non, but it's between carbon 3 and 4. So this would be NON-3-YNE. So the NON means that we have 9. 3 means between 3 and 4. YNE means there's a triple bond. Now, before we're done, we also have to name those side groups, and there are 2 methyl groups, and again, it's just by chance they happen to be methyl. It could be ethyl, butyl, any other side groups that's on your main chain. And 5, 6, 7, 8, and they're on carbon 7. So we would write 7 dimethyl non-3-ine. And now that last example, number 3, we have this line diagram. Line diagrams with triple bonds can be a little confusing because we have to recognize where they are. And linear structures happen with triple bonds. So we have to recognize that there's a carbon at the end. There's a carbon that contains the triple bond. So those 2 carbons. There's a carbon here, and then there's these carbons over here. So you do have your longest chain would be 5, which is pent. And I'm going to start from my left. So 1, 2, 3, 4, 5. If I started from either of these carbons and I started counting 1, 2, 3, I wouldn't get a number for my triple bond until carbon 3. So I want to start on the left so that I give that smallest number possible, which is 2. And then YNE for the ending because it's a triple bond. Now, again, because I'm counting 1, 2, 3, 4, and I'll just say this one's 5, this carbon up here, this is a side group on carbon 4. So this would be 4-methyl pent-2-ine. Now, going back to the last part, which would be to draw it if given the name, it's again the same idea. It's very similar to double bonds. Start with the root, so you have hept. So in this case, we'll draw out 7 carbons, 1, 2, 3, 4, 5, 6, 7. And when I draw mine out, I always number my carbons from left to right, but you can go any direction. It just has to follow the name. So if I'm numbering from left to right, I have carbon 1, 2, 3, 4, 5, 6, 7. I know on carbon 2, so between 2 and 3 is my triple bond. And then on carbon 4 and on carbon 5, I have a methyl group. It just says di because there are 2. So on carbon 4, I'll put a methyl group, and you can go above or below, doesn't matter, just as long as it's on carbon 4. And on carbon 5, I'll do the same thing. Now that my chain is established and my side groups are on, I need to finish off by adding in all my hydrogens. So carbon 1 can have 3 hydrogens. So just always make sure you have 4 lines coming from each carbon. Carbon 2 has 4 lines, carbon 3 has 4 lines, carbon 4 needs a hydrogen, carbon 5 needs a hydrogen, carbon 6 needs 2 hydrogens, and carbon 7 needs 3. And then that one is done. This last one, let's do a line diagram to make it a little bit easier. We have oct, which is 8, and then on carbon 3, so between 3 and 4, you have your triple bond. So we have carbon 1, 2, 3, 4, 5, 6, 7, and 8. Between carbon 3 and 4, you have your triple bond. On carbon 2, you have a methyl group. On carbon 5, you have a methyl group. And on carbon 7, you have a methyl group. And now this one is done. Line diagrams are just a lot faster because you don't have to worry about drawing in those hydrogens. And then this last part is just about properties. So the first part, as soon as you have a double or a triple bond present, you are now unsaturated. So to remember, to be saturated, carbon wants to bond to as many other atoms as possible. So if your carbon is bonded to 4 other atoms, like you would in an alkane, ANE, that's saturated. The minute you have a double or a triple bond, you have to take away one of the bonds carbons or atoms carbon can bond to, and now you are unsaturated. So double and triple bonds are unsaturated. Just like alkanes, all alkenes and alkynes are nonpolar, which means they are not soluble in water because like dissolves like. This point down here, boiling points of alkenes is slightly lower than that of alkanes with the same number of carbon atoms. And they give the reason here, you have fewer atoms, meaning fewer electrons. And if you think back to Chem 20, when we started to take a look at inter and intramolecular bonds, the more electrons you have, the higher your boiling point. So if you have less, your boiling point would lower a bit. And then this last one about alkynes. So notice this one, it says alkynes, so triple bonds, is higher than that of alkanes, even though you're going to have fewer electrons. And this reasoning is because of the linear structure, as we saw in that one example. All triple bonds have a linear structure. And because of that, that line structure, when you have all those compounds coming together, they can pack in really, really, really close. So the closer they are, it's going to be harder to break apart. Whereas the double and triple bonds, right? I don't know why I'm making it look like that. But if you have single bonds or double bonds coming in and you don't have those linear structures, you're not packed in quite as tight. So you need, I don't know what this even looks like. So you need less energy to break it apart. So I hope you found this part helpful. If you did, please subscribe. And if you have any video you'd like me to do, please just leave me a comment. Thanks for watching.